What if everything we think we know about the universe is slightly off? Not completely wrong, but just enough to change everything. What if the expansion of the universe, the very thing that defines time, distance, and reality itself, isn't behaving the way it should? What if two of the most precise ways we have to measure the cosmos keep giving us answers that refuse to agree? And no matter how carefully scientists check the data, the gap doesn't go away. It grows. What if the universe isn't just expanding, but doing it in a way that suggests something deeper is missing from our understanding? Something we haven't discovered yet. For most of human history, the universe was thought to be static, unchanging, a silent stage where stars simply existed in fixed positions stretching endlessly into the dark, but that idea shattered in the early 20th century when astronomers began to notice something. Strange galaxies were not staying still, they were moving away from us, and not randomly but systematically, as if space itself was stretching, carrying galaxies along with it like dots on the surface of an inflating balloon. And this discovery led to one of the most important conclusions in science, that the universe is expanding, and not only expanding but doing so in a way that could be measured, predicted, and understood through the elegant framework of physics and mathematics. And for decades, this understanding held firm, becoming one of the pillars of modern cosmology, a model so successful that it allowed scientists to rewind time mathematically and arrive at a singular origin point, the Big Bang, a moment roughly 13.8 billion years ago when everything began. But as our tools improved and our observations became more precise, something unexpected started to emerge, a small discrepancy, at first barely noticeable, a difference in measurements that could easily be dismissed as experimental error. But as years passed and more data was collected from increasingly advanced instruments, that discrepancy refused to disappear. Instead, it became clearer, sharper, more persistent, and what scientists were seeing was not just a minor inconsistency, but a fundamental tension between two ways of measuring the expansion of the universe. On one side were observations of the early universe encoded in the cosmic microwave background, the faint afterglow of the Big Bang, captured in extraordinary detail by missions like Planck. These measurements provided a value for the expansion rate known as the Hubble constant, derived from the conditions of the universe when it was just a few 100,000 years old. On the other side were measurements of the local universe based on observing distant stars and galaxies, particularly Cepheid variables and Typea supernovae, which act as cosmic distance markers, allowing astronomers to calculate how fast galaxies are receding today. And here is where the problem begins. These two methods should agree. They are measuring the same universe, governed by the same laws of physics, yet they do not. The early universe predicts a slower rate of expansion, while the local universe indicates a faster one, and the difference is not trivial. It is significant enough that it cannot be ignored, and this growing disagreement has come to be known as the Hubble Tension, a name that sounds almost understated compared to the profound implications it carries, because if both measurements are correct and all evidence suggests that they are, then something in our understanding of the universe is incomplete, perhaps even fundamentally flawed. And this realization has triggered a wave of speculation, investigation, and debate within the scientific community, because resolving this tension is not just about fixing a number, it is about understanding whether the laws of physics as we know them fully describe reality, or whether there are hidden factors at play, forces or phenomena that have yet to be discovered. One possibility is that there are unknown forms of energy influencing the expansion of the universe beyond what we currently call dark energy, a mysterious force that makes up about 70% of the cosmos and is believed to be responsible for the accelerated expansion observed in distant galaxies. But what if dark energy is not constant? What if it evolves over time, changing its strength in subtle ways that could explain why early and late measurements differ? Another possibility is that our understanding of gravity itself may need revision. Perhaps Einstein's general relativity, while extraordinarily successful, is not The complete story on cosmic scales and small deviations in gravitational behavior over billions of years could accumulate into the discrepancies we now observe, and then there is the idea that something happened in the early universe, a brief period of exotic physics that altered the expansion rate before settling into the behavior we see today. Some researchers have proposed the existence of an additional component often referred to as early dark energy, which would have briefly influenced the universe shortly after the Big Bang, leaving behind a signature that affects our current measurements. But introducing new components into the model is not simple. Every addition must fit seamlessly with all other observations, from galaxy formation to the distribution of matter across the cosmos, and so far no single explanation has managed to resolve the tension without creating new problems elsewhere, which makes this situation particularly intriguing because it suggests that we are not just missing a detail, but potentially overlooking something more fundamental, something that connects multiple aspects of cosmology in ways we do not yet understand. And this is where the story becomes even more fascinating, because the universe is not only expanding, it is accelerating, meaning that galaxies are moving away from each other faster over time, a discovery that earned the Nobel Prize and introduced the concept of dark energy in the first place. But if the rate of expansion itself is uncertain, then our predictions about the future of the universe also become uncertain. Will it continue expanding forever, eventually becoming a cold, dark void where galaxies drift beyond each other's reach, or will some unknown mechanism alter its course in ways we cannot yet foresee? And as scientists continue to refine their measurements using new telescopes, more precise instruments, and innovative techniques, the tension remains stubbornly persistent. In fact, with each improvement, the discrepancy becomes harder to dismiss, suggesting that it is not the result of error but a genuine feature of the universe, one that is revealing itself only now as our observational capabilities reach unprecedented levels. And this is perhaps the most exciting aspect of the problem, because throughout the history of science, moments like this have often preceded major breakthroughs, times when established theories begin to show cracks, not because they are entirely wrong, but because they are incomplete, pointing the way toward deeper truths that reshape our understanding of reality. And the Hubble tension may be exactly such a moment, to signal that we are standing on the edge of a new era in cosmology, where the next discovery could redefine our picture of the universe in ways we can barely imagine. And yet there's also a quieter, more philosophical dimension to this mystery, because it challenges our assumptions about certainty, about how we interpret data and construct models of reality, reminding us that even our most successful theories are ultimately approximations, maps, rather than the territory itself, and that the universe may always hold aspects that resist full comprehension, at least temporarily. And so the question remains open: why is the universe expanding differently depending on how we measure it? What hidden variable are we missing? What piece of the puzzle has yet to be found? And as researchers continue to explore possibilities ranging from new particles to modifications of fundamental forces, the answer remains just out of reach, like a faint signal buried in cosmic noise waiting to be decoded. And perhaps the most intriguing possibility of all is that the solution will not come from a single discovery, but from a convergence of insights across multiple fields: astrophysics, particle physics, and even quantum theory, each contributing a piece of the larger picture. And if history is any guide, the resolution of this tension may not only answer the question of cosmic expansion, but open entirely new avenues of inquiry, revealing aspects of the universe that were previously hidden from view, because every time we have looked deeper into the cosmos, we have found that it is stranger, more complex, and more surprising than we expected. And there is little reason to believe that this time will be any different. And so, as we continue to measure, to observe, and to question, we are participating in a process that has defined human curiosity for Centuries, the pursuit of understanding in the face of the unknown, and while we may not yet know why the universe is expanding the way it is, the very act of asking that question brings us closer to the answer and perhaps to something even more profound, an awareness that the universe is not just a static backdrop, but a dynamic, evolving system full of mysteries that challenge us to think differently, to look deeper, and to accept that sometimes the most important discoveries begin not with certainty but with doubt.